Hello everyone, it's Benny, and today we're going to be talking about another way of doing binary addition called instant carry addition. Now, first thing you need to know about instant carry is the name is deceptive, because by instant carry, it doesn't actually carry instantly. And it's not actually that different than anything we know so far. In fact, instant carry uses the exact same logic as ripple carry addition. It just uses piston logic to sort of accelerate the carrying process. So really, it's not that different than anything we know. It's sort of just using pistons in an interesting way to make it go a little bit faster. So that's all instant carry really is, and I'm going to sort of walk you through step by step the process of creating an instant carry adder, since we already pretty much know the logic behind it. It's the same logic as ripple carry. So, let's go ahead and get started. Okay, so, just like in any ripple carry adder, the first thing you need is a half adder. Now, I'm going to go with the fastest half adder we've discussed so far, which is the multiplexer-based half adder, which we talked about in the Redstone circuit section. So, first off, I'm going to need to split one of my inputs into just whatever the input is, and its inverse. So the bottom is going to be the inverse, like that, and the top is going to be whatever the input is. And as I'm going to put a repeater here eventually, so as you can see, this just splits it, so the bottom's the inverse of whatever my input is, and the top is whatever my input is. So, yeah. And I'm going to put a repeater here, just because it's going to make the multiplexing a little bit easier. And yeah. So now, as you can see, it's still doing the same thing. But what I can do now is I can put a piston here, and that can act as the multiplexing component. So, now this is my other input. It's the multiplexing component. So right now we have the inverse selected. If I hit the multiplexer, and now select whatever my input is. And as you can see, this changes. And yeah, and it behaves, if I pull that aside so you can see it a little bit better, it behaves just like an XNOR gate. And it's 1 tick, or 1.5 ticks depending on how you use it. So, very nice XNOR gate. But it has a problem. I'm going to put a piston here, and that's going to emulate the eventual piston we're going to have for our accelerated carry calculation. If I, for example, hit this, you notice, it behaves just like you'd expect. If I hit this, it also behaves just like you'd expect. But the issue comes when, what if both of my inputs arrive in sync? Which is a perfectly reasonable speculation. What if they do both arrive perfectly in sync? You'll notice the carry pulses. Or not the carry, the output pulses. And the reason for this is, it takes only 1 tick to change to the inverse, but it takes 1.5 ticks for the piston to extend. So you end up with a very brief pulse, as you can probably see. And as you can see, that causes an issue with the piston. So this is not good. This is really not good. And the reason for this is like I said, it pulses like that. So you have two options here. You can either go with a different XNOR, which is inevitably going to be slower, or you can somehow ensure that the inputs never ever arrive in sync. So, take your pick, but for those of you who want to deal with their inputs might arrive in sync, I'm going to show you another XNOR gate. It's going to be 2 ticks instead of 1.5 ticks, but it's going to ensure that the half-tick issue never occurs. So, let's go ahead and do that. Okay, so for my 2-tick pistonless XNOR, I'm going to start with my inputs like this, and I'm going to OR them together. The way I'm going to do this is I'm going to do it with repeaters like this. So that's my first repeater, there's my second repeater. That's actually on, I didn't realize that, but hey. So yeah. And now if I put some wire here, that's going to take power from here. But if I take a block and I put it here, now we've created an OR gate. A 1-tick OR gate. And if I put a torch right here, this turns into an XNOR gate. Well, it's not an XNOR, it's just a regular NOR gate. To make it into an XNOR gate, what I have to do is I have to make an AND gate. I'm going to have to OR that with the output. Because right now that's the only case it's wrong. So I'm going to take torches like this. This creates an AND gate. And I'm just going to OR these two together. And it's like magic, I have an XNOR gate. A 2-tick, 2-wide tileable XNOR gate. Very nice, and as you can see, if I take my inputs, and I do like this, no derp. Now you do notice that the signal length does change if I do that. It's very subtle, but it happens. And you can fix this just by doing like this. There's nothing wrong with doing this. It does the exact same thing, but yeah. Now, one issue with this. If I make a piston like this, you'll notice, okay, look, it didn't do the derp, right? Nope. And the reason for this actually has nothing to do with our XNOR gate. This is actually a glitch in Redstone. This shouldn't actually happen. But unfortunately, we do have a glitch here, and there's a way that can fix it if and only if your XNOR is facing east, and if you're not near a chunk boundary. So, if we're not near a chunk boundary, this is going to fix it. What I'm going to do is I'm going to change that to glowstone, and I'm going to change the wire to doing like this. And if we're not near a chunk boundary, this should fix it. Unfortunately, we apparently are near a chunk boundary. But just to prove I'm not actually lying to you, if I go over here, you'll notice we have the exact same setup, except for a torch right here, which I can get rid of. And you'll notice this doesn't do it, because this one isn't near a chunk boundary. So yeah. And yeah, so that actually does fix the error. If and only if you're facing east, and if you're not near a chunk boundary. But it's just a glitch in Redstone that really shouldn't be happening, but unfortunately you have to put up with it. So there are a few ways around it, actually. I'm going to talk about them later. I'm actually glad this is near a chunk boundary, because it lets me demonstrate it. And actually I don't know what I'm doing, so yeah. So now, if I get rid of the piston, and I actually put a torch here, you'll notice we have our half adder. This is the XNOR, and there's the AND. So, yeah. XNOR and an AND gate. Exactly what a half adder is supposed to do. So yeah, now we can actually make this into a full-on instant carry adder. Okay, so the first step in doing the carry logic is I'm going to label what my two carry signals are. I have the generate signal, so this is if I'm generating a carry signal, and I have the propagate signal. This is if I'm propagating a signal. And that's the exact same thing I talked about when I talked about Carry Lookahead Edition. So, first off, for the generate signal, I'm going to actually move this to the side a bit, like this, and just because it's going to make it a little bit easier down the road. So, there's my generate signal, and this is actually pretty much done. If A and B, we generate a carry signal. So, there we go. That's already completely done. We can just send this straight into the next half adder. But what about propagate? Now, if you remember, the thing that made it slow is we had this giant series of AND gates. But we can actually do something a little bit interesting. Because what determines if we propagate? Well, that is, if we have a carry signal from before, so this is going to be the generate signal from our previous half adder, and we have the propagate signal. So what I'm going to do is I'm going to do a piston-based AND gate. A transparent piston-based AND gate. And the way this is going to work is if I have a generate signal from the previous one, and I'm propagating, it sends a signal over. So this actually completely does away with that issue. Now, you notice if I turn this off, oh no, it's blocking it again, but that's okay because we generated a signal. And you notice if I turn this off, that completely solves the issue because we're not generating a signal. And yeah, so this is just another way of doing the carry thing. We're doing the exact same logic, except this time we're using a transparent piston-based AND gate. And what that means is if I have, for example, all of these off, I can send a carry signal straight through all the way to the end, because all of these wires will be completely open like this. And yeah, so that's why it's an accelerated carry, because the carry can move straight through with nothing inhibiting it until it hits the piston where it needs to stop. So yeah. And so, at this point, we've completed the carry logic, and now all we need is an XNOR gate at the end. And since we don't need to deal with the weird derpy piston thingamajiggy, I'm going to just use the faster 1.5 tick XNOR. So, yeah. So, there we go. And it's the exact same thing I built before if I'm going too fast. I'm just trying to save video time at this point. So yeah. And, again, doing like this. I'm just going to build it for the next bit too, just because... Actually, that's a good point. Why am I doing that? So first off, I'm just going to delete that. And now I'm going to stack it. So, if I do position 1... Actually, this should be position 1. So position 1... and position 2, and I stack 1. There we go. Now the only issue is I still need to hook up the XNOR to these pistons right here, and the way I'm going to do this is with a staggered line. So, like this, and yeah. And that's because if you remember from ripple carry logic, the propagate line still needs to go into its own XNOR. So yeah, as part of just determining the sum, that has nothing to do with the carry calculation. And so now if I go to this as position 2, and I stack 3, so this creates an 8-bit instant carry adder, in theory. And actually I needed to expand up 1, but oh well. So now I'm just going to connect those manually. And now we have an instant carry adder. So, I'm going to add 5 plus 3. And you'll notice that is derped. So the question is, what on earth did we do wrong? And that is we did not copy our carry calculation things. Our carry torches. So if I just move up into here, and I just do like this, it's going to be like magic, and it's going to work all of a sudden. So yeah. And there's our carry out. And now we've got 8, the proper answer. So yeah, this is instant carry. So the question is, how fast is this? Well, if I turn all of these on, and I connect this to a wire to test it all, in theory, this should carry quote-unquote instantly, right? So, let's go ahead and test. First off, does this actually reach? Yes? Okay, good. So, they're here. Let's start with 4 ticks. And we'll see where we go from there. So 4 ticks, piston, output, and we'll see how far this reaches. And it reaches right here, that's perfectly fine. So this right now is 4 ticks. Let's see what happens. So, it's actually faster than 4 ticks. Is it 3 ticks? That's actually really odd. Is it 2 ticks? Okay, that actually is really odd. This should not be 2 ticks. But okay. Interesting. Very, very interesting, because this... I think there's actually a Redstone glitch going on, because there's no logical reason why this should actually be happening in 2 ticks. But okay. But one thing you might notice is some of the inputs are flashing a bit. And the reason for that... Oh, wait, actually it's 3 ticks, because I'm forgetting to take into account the torch. Okay. Okay, that makes more sense now. But one thing you might notice is some of the outputs are flashing. And the reason for that is the carry issue we had before, the thing with the piston moving. It's making our carry calculation cause a little bit of a flash. So, what I'm going to do is I'm going to hook up all these wires, and we're going to watch it all turn off. So, whoops. There we go. Now this should give us a slightly more accurate idea of how fast it is. And it appears that it actually is 3 ticks. So yeah, we created 3-tick adder, even though with the carry derping, which I believe actually wouldn't even be taken into account in this case. Okay. So that's probably what I want to take into account. Okay. But, you notice, it's 3 ticks for the most part. But once we do the carry derp thing, you notice the piston flashes. And that's a bit of an issue. So if I add an extra tick, still not enough. Actually, I'm just going to add a repeater here. And yeah, see how it's causing a little bit of an extra delay? So this is either 6 or 7 ticks. I'm not going to measure it precisely, but yeah. That's why that's a bit of an issue. Believe it or not, though, there is a sort of a way around it. What you can do is you can actually make the AND gate take 3 ticks instead of 2 ticks. And what this will do is, first off, don't put it there because that's actually going to go through to the carry wire. That's not what you want. So actually I'm going to put it... oh, whatever. I'll put it right here. So, if I just fill all these with repeaters... and yeah. So, almost done. Last one. Now the AND gate takes 3 ticks. And what this will do, in some cases, hopefully this one, it should be in this one. And I don't know why I just destroyed that, because that's just going to make me have to redo it, but oh well. Now, if I test this... actually, wait a second. Why is this on? Why are you on? Interesting. Very interesting. Okay, so I actually think this is a little bit... oh, wait, it's because it's not coming from output of this one. Okay, I'm smart. Okay. So you notice, now, there's none of that flashing issue. Even though for some... oh. Okay, actually, now the flashing is just a little bit quicker. Just because of the way this one works. So I actually need a slightly slower AND gate to fix it. So I'm going to change all these to 2 ticks. And this is definitely not an ideal way to fix it. But if you cannot deal with this happening, if your inputs will somehow arrive out of sync at some point, this will fix it. And one thing to note is you can actually use this exact adder design if you don't have it derping like this at 3 ticks. And I've actually done that before. If you used it like over here where you don't have the chunk error, it works just fine. Now this should actually fix it. So yeah, notice this fixes it. Now all I have to do is I have to figure out how fast that is. I believe that should be 5 ticks, but I don't know, could be wrong. So this should measure 5 ticks. This time the torch doesn't get taken into account because we have a repeater there. So okay, so it actually might be 6 ticks. And okay, so it's actually inconsistent, but okay. You get the idea. It's instant carry is a little bit buggy, and this can cause some really unfortunate errors as a result. But yeah. So, there you go. That's instant carry adder. And this is a pretty good design if it doesn't derp like this, if you build it in an area where it actually works. If you build an area where it actually doesn't do the pulse like that, this actually is a 3-tick instant carry adder. So, very quick. And yeah. One final thing I'd like to talk about is why this isn't actually instant. Because at first you might think, oh yeah, of course this is instant. If I power this, it travels all the way through the completely unblocked line, completely instantly, and hey, wait a second, why is this on? Yeah, it's because signal length runs out. Unfortunately, signal length is actually a part of this form of carry calculation, which might not be obvious at first, but if you think about it, you're relying on the signal being able to travel down every single bit you have. As the signal length travels only 15 blocks, that's a problem. So, since this depends on signal length to actually calculate, in essence, a limiting factor in how quickly you can carry across all bits is the signal length, which is a lot better than 2 ticks per bit for an AND gate. This is more like 1 tick for every 8 bits, so that's about 16 times faster for carry speed, but still, you absolutely need to have repeaters in this for it to work. And there's absolutely no way around it, since you're relying on having somehow a wire that it carries across every single bit, no matter how long it is. Signal length will always be an issue there. And in fact, if you try to find a way around it, you'll find you can't, because these form of AND gates, well, they rely on being too wide like this. There's no way to ever possibly make these any smaller. So it has to be too wide, and yeah. So, unfortunately, this isn't instant because of that. If you look at something like Carry Look-Ahead Edition, at least in the form we did it, that can actually be O of 1. And the reason that can be O of 1 is because it doesn't rely on the wires being a certain length. If you could somehow arrange the logic so that everything happened within the 15 block limit, the carry would indeed be calculated within 6 ticks, or however fast you get your carry look-ahead adder to be. But unlike an instant carry, which relies on the 15 block limit, it doesn't matter how well you organize your stuff. There's physically no way for it to actually happen. And that's why this is still an O of n algorithm. But yeah, it's still much better, in my humble opinion, because you can make this ridiculously fast. In some ways, it's not that much better because you have all these glitches and derps to deal with, but it's still a perfectly good and valid method of addition, and you'll find this used a lot, and it's a very, very good way to do it if you can somehow find a way that doesn't have all the really weird glitches and stuff. This particular adder design is a really, really good one if you build it in a position that doesn't have the pulse glitch, because for some odd reason, it has it in this position, doesn't have it over there, and yeah. But, yeah, so hope you enjoyed, hope you learned, and this is Instant Carry Edition. So thank you, and see you next time.